If not, let me know. That takes us to lesson 3. The inverse of exponential is logarithmic. So we should have a fairly good idea when I said inverse, what that meant. Let me give you an idea. One of the things that we have learned about inverse, that if I have a graph of a function, let's say exponential. Remember what exponential did? Asymptotic, horizontally, wants to approach the x-axis. At 0, it goes to 1. At 1, it went to whatever y equals a to the x. It goes all the way to the a value, whatever that is. -1 was very low. It went to 1 over a, whatever a is. So those are 3 important points about the parent function of an exponential. Today we're moving on to the logarithmic function. So remember what we talked about if it's inverse. We have this magic line, y equals to x. And something happens to a function when we take its inverse. Good morning, Moises. Good, you're feeling better?
Yeah.
Great to hear. So across this line, y equals x, is the inverse of this red function. And it'd be cool if somebody in this room remembered what happens over this y equals to x line. Anybody remember what happens? What does the inverse look like? There's one word I'm looking for. Starts with the letter R.
It's reflected.
It's reflected. Who was that?
Mariana.
Mariana. Remind me today to send you some points. Okay, your way. Very good. It's a reflection. So I'm going to reflect this picture. Now, here's interesting. If the original function was asymptotic to the x-axis, the inverse is going to be asymptotic on the y. Because when you flip this motion, it's going to be down here. That's the reflection over the y equals x line. And 0, 1 becomes basically 0, -1. And 1 comma a becomes 1 comma -a. Okay, so basically everything is, well, actually I'm wrong. It doesn't flip that way. It's going to still be up here because it's got to be just a flip down here. So I got to rethink my thought how I say that. It's not. And what happens is the red is going to go up forever, and the yellow is not going to go up forever, but it's going to go out forever, just like this looks like it's going out. And that's the picture of the log, y equals log base a of x. So that's what a log looks like. Okay, so let's talk about it. I mentioned that we're doing logarithmic equations. That means just like in exponential, we'll solve them. Okay, we'll solve a logarithmic function. We graph them. And we don't graph equations typically. We graph the function y equals. Equation means you're solving it for x. Logarithm, just like exponential, has a base, and the argument's the variable, like in this case x. Okay, so let's see. For all real numbers y, and all positive numbers a and x, where a is not equal to 1. That's very important. we don't think about those things. Let me check if anybody's waiting. No. Okay, so if I'm looking at this function, y equals log base a of x, he has something here that it's equivalent to this function, which is exponential. It's not equal, but there is a relationship. So our question is, how does a log become equivalent to this? I'm going to show you my trick that got me through much of my high school, and when I took my teacher exam, a lot of math, you forget if you're not using it. This is what I wrote down in my notes on the top of my test when I got to this section that was logs and exponential. I wrote this down. I wrote 10 squared equals to 100. I think you can all agree with that. That's exponential. Now watch me write its equivalent equation for a logarithm. I just memorized because I didn't really know what it meant. I'll be honest with you. When I first learned it, our teachers didn't teach us why we do things. We just did them. So I remember doing this. Log base 10 of 100 was equal to 2. Using the same values that I had up in the top equation. I understood this. I really didn't understand this, I'll be honest with you, when I was younger. I just did it because the teacher told me to. Now I understand it, because I'm old now. But watch. If 10 squared is 100, which you all agree, I can turn that to a log with the same base. Now this is my base. So now my base came down here. Log base 10. And since the answer to the exponential was 100, the answer becomes the problem. Log base 10 of 100. And since in exponential the 2 was my exponent, the answer to a log is an exponent, so that's why the 2 goes here. If you could remember this little thing, and I ask you for, here's log base 3 of x equals to 50. And we say, I don't know what that means. Okay, well, you're in good company. Most people don't. But they do understand exponential. So then I say to myself, what's the base? 3. What was the answer to this log? It has to be an exponent. 3 to the 50th. What was the problem? It became the answer, x. Oh, 3 to the 50th is x. I don't know what 3 to the 50th is, but you guys have a calculator sitting next to you. Somebody could tell me what x is by taking 3 caret 50. Does anybody want to volunteer that? I know it's huge. Nobody. Okay, moving on. That means either we're not in the room and you're not picking up a calculator and you're just watching me work. Okay. So by knowing how to switch back and forth to log to exponential, it actually makes your life a little easier. The expression log base a of x represents I think what he wants to say is exponent to which the base a must be raised. Yes. Log is another name for exponent. Just get that through your head. The logarithm means what is the exponent. Okay. So we take all of these problems that are given to me, I can rewrite them really quick. Base is 2. Exponent is 3. Has to be 8. Oh yeah, that's true. 2 to the third is 8. 1/2. 1/2 is my base. Exponent was -4. Is it equal to 16 is my question? That doesn't look so easy. Let me see, what does 1/2 to the negative 4 means? It means 1 to the negative 4 over 2 to the negative 4. The negatives mean the denominator becomes a numerator, the numerator becomes a denominator, and that turns into 2 to the positive 4 over 1 to the 4. Oh, 2 to the 4, 16. Yay, it works. This wasn't as obvious as the first one because we don't want to have to think that hard. Okay, base is 10. 10 to the exponent must be 100,000. Well, it is, because 10 raised to the 5th power means there has to be 5 zeros. 10 times 10 times 10 times 10 times 10 times 10, I think. So there you go. There you have it. Now he's going the other way. Turn these into logs. What's my base? So it's log base 3 of what must be of the answer. 1 over 81 has to be a negative 4. And if you're not sure of that, it's a fraction. So of course the negative has to be on the exponent, because 1 over 81 to the negative 4 really means 81. I'm sorry, I messed up here. It was 1 over 81, that's what it was. 1 over 81 has to be a negative 4. And the only way that's going to happen is if you realize that something is being raised to a negative power to be down here. So that's why it's a 3. Yeah, why am I doing 1? It has to be a 3 power. The base was a 3. 3 to the negative 4. So that's 1 over 3 to the 4th, which is 1 over 81. It wasn't equal to this, whatever that number is. 5, okay, that's an easy one. 5 to the 1. Log base 5 of 5 is 1. Okay, memorize that. Whenever your base is the same as what you're taking the log of, it's always going to be a 1. Because 5 to the 1 of 5, you're asking yourself, what's the exponent? 1. Here's another one that is important to memorize. Something to the 0 power. It really doesn't matter what something is. Anything to the 0 power is always 1. But when I rewrite this problem, I would write log, the base was 3/4 of 1, has to be 0. Well, the log of any base with a 1, the log of 1, it doesn't really matter what that a is, it'll always be 0. So here are two ones that come up often when you least expect it, and it's nice to understand where it comes from. Now we're going to solve logarithmic equations. So we're going to undo what's been done. I have a hard time solving a log equation by keeping it in log. Remember what I told you? All through high school, I had no idea what it meant. Maybe even half of my college, I didn't know what it meant. Not really. Oh, I could get the answers. We didn't have calculators like you had. I think we had logs, base 10, that's it. And we had ln. ln is log base e. It's the same thing as log base e of something. ln of x means log base e, which we haven't talked about e too much. So write this as an exponential. The base exponent equals 8 over 27. Interesting. What to the third could possibly be a fraction less than 1? Well, since I don't really know for sure, I'm just going to do what I know to do to solve for x. I need to undo cube. So I cube root. I cube root both sides. Cube rooting x cubed leaves me the x, which now leaves me basically the cube root of 8 over the cube root of 27. You should know What times what times what is 8? 2. What times what was 27? 3 times 3 was 9. 9 times 3 is 27. 2/3. That's why we got a fraction. We got a fraction to a power could give me a fraction. Yeah, that makes sense now. Let's continue this madness. Turn it into exponential. 4 to the 5/2, whatever that means to you, has to be the x. Now that looks kind of hard. How am I going to get rid of that? I don't have to get rid of nothing. It's already done. That is the answer. X is x to the 5/2. But let's see if we can get it simpler. Recall that x to the 5/2 means or something to the 5/2 means that 4 here is being raised to the 5. Or you could say that 4 is being square rooted. Either way you want to do it. I'm not sure what you will do. You'll probably be thinking of 4 to the 5th. And then take the square root. That's what the answer is. The square root of 4 is there 5 times. So if you think about it, this is the square root of 4 times 4 times 4 times 4 times 4. That means it's a square root of 4 times 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 square root of 4. I'm doing a lot of steps to show you that you don't need a calculator. I know some of you cheated already. No, you probably didn't, because I don't even know how many of you are in the room. 4 caret 2.5 will give you the answer. 4 caret 2.5 is the answer, but I'm doing it without a calculator because I recognize a square root is that denominator there. So I'm taking advantage of it. 2 times 2 times 2 times 2 times 2 is 32. So that's what x is, 32, without a calculator. Mic drop. Yeah, that's what I want to do. For anybody who's listening. Well, Moises is listening because he's stuck with me. He's stuck in the room.
The mic drop.
Huh?
The mic drop.
The mic drop, yeah. You're the only one that probably got the blessing of it. So let's talk about the graph. I already gave you a hint. Look at that. I already gave you the hint that the exponential's inverse is this beautiful logarithmic function. And so he created a whole bunch of x's to plot. He used his calculator, and he's using a base. He used a base 2. Well, I'm going to give you your shortcuts, guys. 3 points. Remember with exponential, we had 0, 1 exponential. That turns into 1, 0. This is exponential, and this is log. So there's your 1, 0. Ta-da! In exponential, we had 1, a. But in logarithmic, we have a, 1. So a, 1 right here. He went over a up to 1. Now I was trying to do the other one a minute ago. Exponential, we had a -1. That's where I forgot to write down. -1, that's where I messed up. -1, 1 over a, because on the exponential graph, it was a -1 not very far up. Well, I had that on the picture, but I didn't think about it being a -1. I think I said it, but I didn't think about it. So at -1 has to be the x value. Well, where was it? That's the x value of the exponential. In log, it's go over 1 over a, go to the right just a little bit, and then go down 1. So he went over a little bit, down 1. So if you have those 3 points on your parent, you can just simply realize that it's asymptotic this way, and then going up this way, it's going to go up and over forever and ever and ever. So there's your parent. I don't care if it's log base 2, log base 5, as long as a is a positive number, okay? So just look at that picture, a domain. The domain is what the exponential's range was. If you remember, the exponential range went from 0 to infinity. So that must mean the domain, this was the range of exponential, the domain of the log must be from 0 to infinity. Now the range used to be the domain of exponential. And the domain for exponential was all real numbers, because remember, it did this, all real numbers from the left and to the right. So the range this time will be all real numbers. I heard somebody just log off, so be warned, you have to check in on the chat or I'll never know you were here. So we would write negative infinity to infinity. Same thing as all real numbers. That's your range. Goes down forever and go up forever. Okay? If f of x is some sort of logarithmic with a being greater than 1, the function is going to be, I'm going to say continuous, because I don't know what else the author had. I had that same question before. It's definitely continuous, and it's definitely increasing on the entire domain of 0 to infinity. It constantly gets higher and higher and higher and higher and higher and higher and higher as you go from left to right. The blank axis is a vertical. The y-axis is a vertical asymptote as x goes to 0, which means the limit as x approaches 0 of my f of x, whatever that is, will be negative infinity. I'm just giving you this extra thought. The limit as I approached x, as x approaches 0, there's something else I should put in there that might be way over your head because it's calculus. When I'm approaching 0, I'm approaching 0 from the right. So I put a plus sign there. That means I'm approaching 0 from the right. Because obviously, if you look at the picture, I can't approach 0 from the left because there's no function over here. I can't approach from the left. I can only approach 0 from the right, and I'm approaching the y values way, way, way down there. The y-axis vertical from the y-axis is a vertical asymptote from the, oh, right. I guess if I would have read that first, I might have acted smarter. The graph passes through these points. 1a, a little bit over to the right, you're approaching a negative 1. That must be who accidentally got kicked off. At 1, it was an a, and at, yeah, 1 was an a, is that what did I say before? 1 was an a, yes. Hold on here. 1 was logarithm. I don't think I marked it, or did I? I have. Oh yeah, 1 was a 0, not a. I knew it didn't sound right. 1 was a 0, but nobody yelled at me. The a gave me the 1. Yeah. Sometimes I think I'm all by myself. You know how I can prove it? I'm half by myself. If I just miss class right now, I'll look at the screen, I'll put the pictures back up. Half of you will still be sitting there. So sad. Your other teachers have noticed too. New problem. What if a, what's he doing? How do you flip a function? How do you flip the function from going like that to flipping to upside down? Somebody prove to me you're in the room. How did it happen before? Somebody. Well, in this case, since I don't know if you're here, if a becomes a fraction, it flips over. So the only thing happened is, actually I think he did something else. he put a negative somewhere. I don't see where he typed it in. Well, he's not showing it. All right, let's look at a fractional a. We did look at those in the other problems. Log base a half of x equals to, I don't know, 4. You could solve that by saying 1/2 to the 4th is x. X must be 1/2 times 1/2. That's 1/4. 1/4 times 1/4. 1/16. Very small. So if you go 1/2, it would be this problem right here. See, if my a is 1/2, at 1/2 I go up to 1. At 1 I'm at 0, and at 1 over 1/2, which is actually a 2, 1 over 1/2 is actually a 2. That gives you 1 over a will give me a 2. There's my third point. He gave, there it is, look at that, 1/2, it's down, I'm sorry, -1. It's there, -1. At 1/2, positive 1/2, he's at 1. At 1, he was at 0. And at 2, he's down to the -1, because those are those 3 points. He has some extras here that I won't really need unless you like to do tables. And let's look at the picture. Oh, same picture. And we can say the domain is obviously from here to here, but it can't be the 0. So 0 to infinity. The range obviously goes up forever and down forever, so we say -infinity to infinity. The f of x equals log base a of x. For the a to be a fraction less than 1, the function still is continuous, and it still is, now it's decreasing. Oh, when a becomes a fraction, it becomes decrease. Oh, remember when we did exponential? 1/2 to the x equals my function was an exponential decay. Remember that? It also was decreasing as an exponential. And as a log, it's decreasing as well. That's pretty powerful thought. The y-axis is the vertical asymptote as x approaches 0. So what we could still do the limit as x approaches 0 from the right if you wanted to, and see that it's still going to be a positive infinity. The point passes through 1 over a at -1. Was that right? Somebody? Yes, there it is. Thank you, Moises. At 1, it's a 0, because 0, 1 was the exponential. And then at a comma 1 is the 1 comma a switch. So that's everything you need to know about graphing exponential. That'll get you through everything you're going to need. So here we go. Graphing them. You could cheat and just use your calculator. I understand people don't want to think too hard, but I'm going to try to do these without my calculator. And since this a is less than 1 but greater than 0, I know the 3 points I need. I need 1 over a, which gives me a -1. I need a 1, which gave me the 0. And I need the a, which gives me the 1. That's all I need. Those are all I need. And here a is a half. So I'm going to go 1 over a half. 1 over a half is going to be a 2. 1 divided by a half. How many halves are in 1? There's 2. Or you could do 1 divided by a half is 1 times the reciprocal. Same thing. Okay? So 1 over half, that's a 2. So what I got to do? A is a half. What am I plotting? Let me do 1 over a first. 1/2 real small, go up 1. 1 comma 0, there's a 1 comma 0. And then when I plug in 1 over 1/2, I'm supposed to get, oh, I'm sorry, I put the answer of a 2, but that's not what goes in this point. That was a -1. 1 over 1/2 is a 2, negative, there it is. 2, -1 is down here. So, if people would tell me that I wrote something wrong. So there's my curve, smooth curve going this way, going up, asymptotic to the y-axis. That's about as good of a picture I could ever make, because I'm just not an artist. And your calculator probably gave you something very similar. Okay, now my a now is a positive number. Oh, it's still they're both positive, but it's bigger than 1. So that meant we're using, well, we're still doing the same thing. We're still going to say 1 comma 0. We're still going to say, what was the other ones we did? We did 1 comma 0, 1 over a -1, 1 over a -1, and we did a was a 1. So if a is the 1, 0 is always the same, so I'm just going to put 1, 0 right here. We'll do blue. 1, 0 right here. There's 1, 0. That's that one. 1 over a with 1 over 3 is very, very small, 1/3, and go down 1. So that goes down to here. And here, 3 comma 1, 1, 2, 3, 3 comma 1, that's over here. Oh, remember when a was bigger than 1? It's increasing forever instead of decreasing. And this I probably could do better. There. Asymptotic to the y-axis. That makes sense. That's a pretty good I'm off a little bit. Close enough for the government, though. Any more on this page? Nope. Moving on. Okay, you got more graphs. Oh, we're going to move them. Okay. Don't fear. Don't fear. You know how to do this. Everything we've learned before is the same. If we're doing log base 2, just the parent, y equals log base 2 of x. That's the parent. Remember what we did before. Go ahead and graph the parent first. 2 is positive and it's bigger than 1, so it's going to look like this. That's what it's going to look like. We know what the points are. Was 1 comma 0, 1 comma 2, 1, 2, and we know we have to have 1 over a, which is 1/2, comma, -1. I keep putting the wrong number there. It goes to 1. I think I have to put it right. Let's see. What points was I doing? A was a 2. It was 2 to the 1. Yeah, okay. 2 to the 1. There it is. There's 1/2 to the -1. 1/2 to the -1. Those are my 3 points. Why am I spending time labeling those points? Because I want to see what's going to happen here. In the past, anytime we subtracted 1 from the x, think of your parabola. Y is x squared. Y is x minus 1 squared. What did that -1 cause the function to do? Somebody. Next clue. Does it move up, down, left, or right? Does this parabola move down, or right, or up, or left?
To the right.
It moves right. Who was that?
Irene.
Irene. Same thing as Miss Hefferman. Let me know if you want some points. Thank you, Irene. It makes me so happy when I know somebody's actually there listening. And I have 20-something of you in here, almost 30 people, and I only hear from 3 people. And then people don't get counted present, and they want to say, hey, I was there. Well, you couldn't prove it by me. Just because I see your picture doesn't mean you're there. So it's going to go to the right. So this point has to go 2 places to the right. I'm just going to graph what the picture might look like. Boom, 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 something like that. Whoop, that's too far. It's going to look like that. There is my answer. Now, the only thing I want to stress with you, if you want the author to believe you know what you're doing, remember my asymptote. Guess what? It moved also the right. How far was I going? I think I went too far. I went 2, but nobody said anything. Let me move that back. Wish I could move it back without doing any work. I moved it twice. I thought it was x minus 2. It only goes right 1. So boom, boom, boom. And then the asymptote also goes right 1. So technically I need to make sure that if that has to go over 1. So the function is looking like that. Everything goes to the right one. All right, I spent too much time. What happened if I take a function like y equals x squared and I subtract 1 from the whole thing? What does it do? While you're thinking, I'm going to figure out what y equals log base 3 of x looks like. No surprise. It looks a lot like the last one did. The values just changed. That's all. It looked like that. Looked the same. Just the number is a 3, so I still have 1, 0, but now I have a comma 1. So at 3, it's going to be steeper actually, because it's going to go higher. I mean, it's 3. It's still going to go up to the 1. I'm sorry, but that's a 3, so it's not a 2. So I don't know what makes it a shrink. And then the negative 1 is where I'm going to have a 1/3 there. All right, you had time to think? What does it do when I take 1 away from a function?
Shifts down.
Say it again?
Shifts down.
Goes down. Thank you. Is that Rosalind?
Yes.
Okay, same deal with you, Rosalind. And so, and I won't remember these guys. You guys that's like 3 of you already today. I won't remember. You're going to have to make sure you message me later. So every point goes down how much? 1. So I'm just going to do government work. I'm not really labeling the point. That point goes here. That point goes down here. That point goes down here. You change those to the color. Black. That point went down. Where did I put it? Here. No, that's too far. Here. That point went down here. Okay. So it looks almost the same picture, except everything shifted down 1. Did the asymptote move? No. Asymptote's still there. It's just going to take a little longer for this one, to hit the asymptote, or not hit it, but get closer. Okay, that was fun. No more? Oh man. Okay. Properties of logs, very important. It's the same thing as your properties of exponents. X to the second times x to the third. Like bases, we add the exponents. X to the fifth. The answer to these are exponents. So I can add exponents, which means if a log is an exponent, I can do log base a of x plus log base a of y. I add the exponents, 2 plus 3. That's what this meant, 2 plus the 3. When you multiply inside a log, it's the same as multiplying like bases. Multiplying like bases, we add the exponents. What do I do when I divide like bases? We subtract the exponents. So I can break this up into 2 logs with subtraction. What about a power to a power? X to the 4th raised to the 3rd. A power to a power. This is a power to a power. We multiply the exponents. So in this case, he's multiplying the 2 exponents. That means that exponent that you see above the log problem can go to the front. We already talked about the log of 1 is always 0 because of the ordered pair, 1, 0. We've already talked about this property. That's what this means. We already talked about that the log base A of A is 1. We've talked about that. That meant 10 to the 1 equals 10. We've talked about that. It's a property you can use. Okay, I hate when he wants me to fill in descriptions. I do need your help. The logarithm of the product of 2 numbers is equal to the sum of the 2 logarithms. The logarithm of the quotient of 2 numbers is equal to the difference between the logarithms. The logarithm of a number raised to a power is equal to the exponent multiplied by the logarithm. That's this r times the log, if that's an r. The base A logarithm of 1 is 0, and the base of a logarithm of a logarithm, base A logarithm, that is, base A logarithm of A is 1. I don't know if those gray boxes help you or not, to be honest with you. I think some people who are paying attention, I think the examples help them more than... let's use it. Okay, I'm going to speed it up because how much do I got left? I got properties. I should get most of it, enough to call it good enough for government work. Here goes. We would write that as keep the same base plus keep the same base 9. It's the same thing as saying log base 6 of 63. That's the same answer as all of that. This becomes log base 9 of 15 minus log base 9 of 7, which is the same as log base 9 of, well, whatever, I don't know what that is, 2 point something, whatever that is. Let's continue. Okay, think of this as log base 5 of 8 to the 1/2. There you go. You see what happened? Square root means the exponent's of 1/2, so guess what you can do? You can write 1/2 log base 5 of 8 if you wanted to. These are just things you're allowed to do if you want to. And trust me, in the future, sometimes you have to do a property of logs to make it usable. The exponent here, log base A, would be m over 3. That's what cube root means. It's the denominator is a 3. That means that, what did I write m? It should be, it's m squared, so it's 2/3. So it's m to the 2/3, so that would be 2/3 in front, log base A of m. Oh my gosh, you got a lot of stuff going on. A lot of stuff going on. I got adding 3 of them, then subtracting 2 of them with powers. So that gives me the log base A of an m plus a log base A of an n plus a log base A of a q. All of that minus these ones. So put them in parentheses. 2 log base a of p plus, is that a 4? Log base a of t. There you go. That's a pretty good answer. Now, if you want to distribute that minus, you could say minus that, minus that. I'm running with that, though. Okay, first thing. Log base b of something to the 1 over n power. That's what that means. And I have an x cubed, y to the 5, z to the m. Get rid of this power up here. Put that in out here in the side. Log base b of 3x. So that 3 technically can go in front of the log and put the x plus that 5 can go in front of its log base b of y. And you know what I might do is put a parenthesis around all of that, just because that's my numerator. And then I'm going to do my minus. And the reason there's a bracket is because that 1 over n is the whole thing. That 1 over n is the whole thing. Minus, that was z to the m, so the m log base b of m. And there's only one term, so all I got to do is just close it. Oof. That's a lot. Reverse. Let's see. Put them back together if you can. You cannot break apart a sum inside. If it was a multiplied, you could. But this is stuck. You cannot simplify that. These two have the same bases, so I can make it a plus. How am I going to do it? It's minus. So what am I adding? I'm adding a quotient. I'm adding a log base 3 of x over 2. That's the best I can do with that problem. You can't put these together because this inside can't be broken apart. I think that's a trick question. You can break, if you had 2 logs and you were adding the 2 logs, then you could log of the product, but you couldn't do what that is. Always check for the same bases. They do. It's minus. That 2 can become an exponent on the m, so I'm going to look at log base a m squared divided by log base a of n cubed. I don't like doing these. I got a same base, same base, same base. If it's not the same base, you can't do it. I got a plus, so that's going to give me a product of 1 log. Is being added first. It's the order of operations. That gets done first, and you're going to have the log, you're going to have a division in there. So my log base b of the square root of m, that's what m to the 1/2 is. Then I have log, that's going to give me log base, that's still log base b, but I have 2n, both of those raised to the 3/2. You could write that differently. I'll write that in a minute. Divided by this, log base b of m squared n. If you wanted to, all of this, the only thing I could do differently was write log base b. You could either make them both exponents with fractions, or you could say square root of m square root of 8n cubed, because 2 times 2 times 2 is 8, and it's a square root Oh, wait, and the n also got n times n times n cubed over m squared n. You could do that. There's a lot of ways.
Sure.
You can't break addition inside a log.
Sir,
Yeah,
could you go back and zoom out? I forgot to copy one step.
I'm sorry. Thank you for talking. Appreciate it.
Okay. Thank you.
You set?
Yeah.
Thank you very much. You made my day, Rosalind. You made my day. Someone's here. Um, he's just saying if you could. In the old days, we didn't have a lot of calculator stuff, so somebody had to tell you what log base 10 of 2 was. That's a decimal that we used to memorize that. We'd also memorize log base 10 of 3. That would help us a lot. So that way, without a calculator, you knew that this was the same as log base 10 of 2 squared, which meant 2 log base 10 of 2. So there's your log base 10 of 2. 2 times 0.3010 would give you your answer. Without a calculator, in the old days, that's all we didn't have fancy stuff like you guys have now. How can I do that? Oh, I got it. Watch this. Watch this. Log base 10 of, I call this 10 divided by 2. Haha. Yeah, this will work. Watch. Watch. Log base 10 of 10 minus log base 10 of 2. See that? I mean, I'm pretty proud of myself. That's a log base. Make it smaller. So log base 10 of 10, everybody, come on, is 10 to what power is 10? 1 minus 0.3010. Yeah, 3010. So that becomes easy with the calculator. Oh, I'm so proud of myself. Do I want to mess with this? Well, that's interesting. Yeah, a to the log of a cancels each other out, because a to the x and log base a of x, they're inverse of each other. So whenever you combine the two inverse functions, like squaring a square root, it cancels it out. So it's the same thing happens. This just gives me, I think it just gives me, that's a good question. What does it give me? It says x equals to x. I don't know what else I can put. Yeah, I don't know. And log base 10 of a to x gives me x log AA. Log AA is a 1, so it gives me x equals x again. I think he just wants you to realize that whenever you see a to the log of a, that really all cancels, leaving whatever is here. It was a log a of 5 equals to x, then that's the exponent. That all goes away. That means x is 5. So that's why they're showing you that. And we did it with no minutes to spare, right on time. So guys, have a great